20. In this lecture, we will introduce a data structure for maintaining disjoint sets. So the data structure will support two operations, namely the union operation and the find operation. So for this problem, there are actually different methods. The first one that we will introduce now is using the linked list. And then in the next lecture, we will talk about another method which uses the rooted trees. Okay, so first of all, what is the problem about? So consider the following dynamic graph problem, where from time to time, a vertex can be added to the graph, an edge can be added between two existing vertices in the graph, and then from time to time, we also want to check which connected component contains a certain query vertex. We want to maintain this changing graph so that we want every operation here to be operated efficiently. So how can we do so? Now this problem corresponds to maintaining a collection of disjoint sets where the operation of the following will be supported. So first of all, we want to have this mixed set operation which creates a set containing an item x. So this item x will refer to the vertex that is going to be added into the graph from time to time. And then we want to support the union operation, which takes x and y as the parameter. So for the union operation, we will merge, we will combine the set that contains x and the set that contains y, and then combine them into one bigger set. So in this case, we are going to relate this to the creation of an edge joining two existing vertices x and y. So in that case, the two vertices, after joining them, they will be in the same connected component. And so does the original vertices that are linked to x and the vertices that are linked to y before. So they are all now going to be in the same connected component. So we are going to make them into the same set. And finally, we want to support the find operation. So in the find operation, we want to return the label for the set that contains x. So here, it corresponds to finding which connected component contains x. Okay, so usually we talk about the labels here. So how do we choose the label? So usually each set will pick one of each item to be the label. Now if this is the case, then to check if two items x and y they are in the same set, then we can just perform find x and find y, so that we can look at the label for the group containing x and the label for the group or the set containing y and check whether they are the same. If they are the same, then they are in the same set. Now different methods uses different ways to search for the labels in the find operation, and because of this will also affect how we perform the updates in the union operation. Yeah, because when we do union, the relationship between the sets may change. So some sets will be combined into one. So some of the items may need to have a new label. Okay, so a very simple way to maintain disjoint sets is to use linked list. So for each set, we are going to use a distinct list to represent it, and the set label is set to be the head item of the list. Now, if we want to support find in constant time, we can do the following. So each of the item in the set will have an extra pointer that points to the head item. And then we also have a tail pointer that points to the last item of the list. So in such a case, then we can do something that is fast later for the union operation. So basically, this is a diagram showing what could happen. So in this case, we have three lists. So we have the list containing A, B, C, D. So we assume that these 4 items, they are in the same set. And then A is the head item. So this is also the label of this set. And another set contains the items E, F, and G, and E is the head item. And finally, a third set contains H. So H is the single item, and it is also the head of this set. And now to perform union of two items, X and Y, we just find out the list containing X and the list containing Y. And this is going to be very easy because from X, we can trace the head pointer, and from Y, we can also trace the head pointer. And then we get the corresponding list, and then after that, what do we need to do? So we are going to update the pointer of the head for each item in the letter list. So what does that mean? So for instance, suppose that we perform union of G and H in the previous example, so G and H. So we want to union G, we want to union H. So from G, we got this list. From H, we got this list. So in that case, we combine the two lists into one. So it is very easy. We can make one list to be appended after the other one. So in that case, we could put H after the tail of the list containing G. So we are going to put H here. So in that case, we can combine the two lists into a single list. And after that, we relabel the head pointer of H here because H is the one that appears in the letter list. So we update the head pointer here. So this is done for the union operation. Okay, now suppose that there are n items in total. The worst case time to perform each operation will be as follows. So for mixed set or find, then it is easy because it takes constant time. Now for the union, it could take order n time. The reason is that when we perform union, we may be combining two lists, one after the other. So the letter list could be like having a lot of items. So in that case, each item, we need to relabel the head pointer. So imagine we have two lists already. Each one of them is like n over 2 items. So in that case, no matter which one is the letter list, we need to update head pointers order n times. So in that case, the union operation takes order n time in the worst case. Now because of this, for m operations, the worst case total cost will be m plus n squared. Now, why do we have just n squared here? The n squared corresponds to the time that we perform union. So altogether, each of these items can be relabeled at most n times. So the total time for the union operation over any number of operations is at most n squared in total. So when there are m operations, then it could be like mixed set or find m of them. And then for the union, no matter what happens, it is at most n squared. So the total time in the worst case is m plus n squared. Now, let us consider a following heuristic to perform the union operation. So when we perform union of two lists, we shall put the longer list first. So that will be very helpful because only items in the shorter list will need to update the head pointers. Now, using this scenario, we claim that the total update time is at most order of n log n for the union operations. The reason is that each item, when it performs the head pointer update, it is going to be located in a set that is more than or equal to the double of its original set. So for instance, this H and this EFG, when we perform the union, we will put H as the letter list because the list containing H has only just one item, but the other list has 3 items. After the combining of these two lists, H will be relabeled. And then after H is relabeled, the, the size of the set containing H changes from 1 to 4. And in any case, the change will be from 1 to at least 2 times of 1. So every time when it is relabeled, the size of the set containing an item that is relabeled needs to be at least doubled. So in that case, the total number of updates for a certain item can be at most log n times. So in that case, the total update cost using union in this heuristic is at most n times log of n. N items, log n at most for each item. So in that case, if we have m operations, then the total cost or the total time will be m plus n log n for any number of operations. But we notice that m has to be always greater than or equal to n, because in order to have n items in our picture, there must be n mixed set operations. So in that case, the number of operations must include at least the same number of items that we are considering in the set. So m includes at least n of them, which is the mixed set operation. So we must have m greater than or equal to n. Now, because the total cost of m operations is like this, and then m is greater than or equal to n, then we know that the amortized cost is at most order of log n time. And equivalently, we can view the linked list implementation as the following scenario. So we can think of each list as a rooted tree of height at most 1, so that the root is corresponding to the head pointer, the head item, and then each of the other item is the child. Okay, each one of them is a child of the root. So the first list corresponds to this rooted tree, the second list corresponds to this rooted tree, and the third one corresponds to this one. So in that case, so we have this scenario, and then find can be supported in constant term. That is very easy because we just find out which item is in which tree, right? And then we trace the pointer going to the roots, and then it is at most one step away. So find can be performed in order one time. And then for union operations, so for instance, when you union G and H, then we compare the size of these two trees, the tree containing G and the tree containing H, and we relabel the size and relabel the tree with a smaller size, each of the nodes there, and make it a child of the other tree as root. So we have this scenario. So in that case, this is an alternative view of the linked list implementation, which is actually some kind of a rooted tree implementation. So that's all for this lecture. Thank you.